Yeah, welcome students. I am really happy to see you to discuss this traveling salesman problem. So actually, traveling salesman problem is a maximization problem in the assignment procedure. The Hungarian method, almost all of them are minimization problem, but this is a maximization problem. Okay, so our optimum is maximum among maximum. That's what we have to give importance there. Okay, right. Traveling salesman problem. Now I'll take one problem and we will discuss that. Suppose there are four salespersons are there, S1, S2, S3, and S4. And there are four districts are there, D1, D2, D3, D4. Four salesmen and four districts are there. And the figures inside the box, the green color box, gives you the profit they are bringing to the company. I mean, if the first salesperson is sent to the first district, he is bringing 16 rupees for the company. If the first person is sent to the last district, he is bringing 11 rupees to the company. Suppose the fourth salesperson is sent to the third district, he is bringing 13 rupees as the profit to the company. So the intersection of the rows and columns gives us uh, the profit that corresponding person coming from the corresponding districts. Okay, so this is about a traveling salesman problem. The salesmen are traveling to different districts, and which salesman should be sent to which district so that the total transportation cost is very maximum. That's what our primary goal, primary aim here. Okay, which salesperson has to be sent, which salesperson has to be sent to the which district so that the total income is a maximum for the company. That's what our aim here. Okay, so according to this method, um, we have to make this a maximization problem, a minimization problem. Okay, this is a maximization problem. We have to change into minimization problem. Okay, how we do that? How we do that? How we do that? Okay, so in this particular mesh or in this particular what can I say, tabular form or in this particular matrix, okay, which is a very maximum number, which is a very maximum number, that number we have to identify. Okay, here look at this particular mesh or particular matrix structure. 16 rupees, 15 rupees, 10 rupees, 11 rupees, 14 rupees, 13 rupees, 12 rupees. So among these, which is the maximum? 16 rupees is the maximum. Am I correct? Right. So this maximum, 16 rupees we have identified. So all these elements here in this particular matrix, subtract these elements from the 16. That is the maximum element in this particular matrix. Okay. You understand what I say. You identify the maximum element in the matrix, that is 16. You subtract the entries, other elements from the 16. Okay, uh, you will get this matrix. Okay, take for example, here 16 is the maximum. So 16 minus 16, 0. 16 minus 10, 6. 16 minus 14, 2. 16 minus 11, 5. 16 minus 14, 2. 16 minus 11, 5. 16 minus 15, 1. 15 minus 16, 1. 16 minus 15, 1. 16 minus 15, 1. 16 minus 13, 3. 16 minus 12, 4. 16 minus 13, 3. 16 minus 12, 4. 16 minus 14, 2. And 16 minus 15, 1. Okay, so now this is a minimization problem. Now, this is a maximization problem. When you take the greatest number among these and subtract all other entries from this maximum number, what the matrix you are getting is a minimization problem. This is a maximization problem, and this is a minimization problem. Okay, so that's the first step in any maximization problem. Okay, or traveling salesman problem, we can say so. Right. Now, what is the next step? The next step is same as we are doing in the minimization problems under the Hungarian method. Okay. So under Hungarian method, what we do, the row reduction we'll do, then the column reduction we'll do, then the drawing line we will do, and whether the number of lines equals the order of the matrix we will check up. If that is the case, then the optimum is reached, then the optimum assignment we do, and that assignment will give definitely the least transportation cost. Okay, so that is what we are going for that. So this is what makes minimization problem. So the next step in the minimization problem is that row reduction. Row reduction means we have to find out least element from each row, and we have to subtract it from all other entries. So this technique I have brought in another video. So you go through the another video. In that another video, I have clearly explained the row reduction, column reduction, drawing the lines, and optimum assignment. Now look at this. The least number is what? 0. So subtract 0 from all other entries. We'll get 0 minus 0, 0. 6 minus 0, 6. 2 minus 0, 2. 5 minus 0, 5. Next row. Least number is 1. 2 minus 1, 1. 5 minus 1, 4. 1 minus 1, 0. 1 minus 1, 0. Next row, the least number is 1. 1 minus 1, 0. 1 minus 1, 0. 3 minus 1, 2. 4 minus 1, 3. The last row, the least number is 1. 3 minus 1, 2. 4 minus 1, 3. 2 minus 1, 1. 1 minus 1, 0. The total process, we call it as a row reduction. Row reduction, we say. Now let us do the column reduction. What we do row wise, we have to do by column wise. That's called column wise reduction. Okay, right. The first column you take now, the least number is 0. 0 minus 0, 0. 1 minus 0, 1. 0 minus 0, 0. 2 minus 0, 2. Next row, least number is 0. 6 minus 0, 6. 4 minus 0, 4. 0 minus 0, 0. 3 minus 0, 3. The next 0 is the least number. So you will get the number as it is. Am I right? 2 minus 0, 2. 0 minus 0, 0. 2 minus 0, 2. 1 minus 0, 1. The last row also 0 exists here. Therefore, same column will come here also. 5 minus 0, 5. 0 minus 0, 0. 3 minus 0, 3. Sorry, 3 minus 0, 3. And 0 minus 0, 0. Column wise reduction over. Now, as usual, what is the next step is that to drawing lines starting from maximum number of zeros. Here, the order of the matrix type, the matrix is 4 by 4. So, maximum 0 possible to occur rows and columns are 4 zeros. Am I right? 4 zeros are the chance that each row and each column can have. So I am looking for 4 zeros rows or columns. If I could find, I have to draw the lines across the 4 zero occurring rows or columns. The first row, no 4 zeros, only 1 0. Second, no 4 0, 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 no 4 zeros, no 4 zeros. Now the next maximum 0 can occur in a row or column would be 3 zeros. Am I right? So I am searching for 3 zeros occurring rows or columns. Any 3 zeros? No. 3 zeros? No. No 3 zeros. No 3 zeros. No three zeros. No three zeros. No, no. What is the next number of zeros? Maximum number of zeros can occur in a row or column? Two zeros. Am I correct? Yeah, first, no two zeros. Second, yes, thank you, Lord. I have two zeros occurring here. Draw a blue line here. Right. Next, third row. Yes, again, two zeros. Draw another line, red line, through that particular row. I have drawn. Last row, sorry, no two zeros. Now come column wise. When you come column wise, once the zero is striked out, you should not take that zero for column wise. So no two zeros, no two zeros, no two zero, and no two zero because this zero is already striked out. Right. Now the next maximum zero occurring rows and columns. Maximum zero is only one zero occurring rows or columns. Yeah, the first one is only one zero occurring rows. Am I correct? So you draw that one line. Then second, already drawn. Last one is green line, all line. So totally, how many lines we can draw? We can draw four lines. Am I correct? So what's the order of the matrix? 4 by 4. So 4. So optimum is reached. Okay. So optimum is reached. Now what is the next step? We have to assign zeros such that each rows and each columns have only one zero. Such a way we have to assign. Now I am taking the first row. Now from this, how this comes? The zero occurring places only we have to take. Zero occurring cells, that only we have to take here. Okay, zero occurring cells. So here is one zero occurring here, another zero, here another zero, here another zero, here another zero, here another zero. Okay. Now first row I am taking there. First I am assigning this. Then this district I cannot assign to S2. I am striking out. Next coming here, the next salesperson I am asking to go to third district. So he cannot go to fourth district, strike out. Then the third salesman, I am asking him to go to second district only. This district I cannot allow him because already assigned to D1. In this type of problems, very important thing is that one salesperson can be assigned to only one district. That's all very, very important assumptions in the assignment problem. Right. So this person cannot be assigned here because already it is assigned to first salesperson. So second per salesperson only we can assign. Now coming to the last salesperson, uh, only one available district, the last district. So the S4 can be assigned to last district. So this is the optimum assignment. That is first salesman to the first district, second salesman to the third district, and third salesman to the second district, and last salesman to the last district. Okay, so this is definitely an optimum assignment because that definitely will give us an optimum assignment for us. Okay, so if we if we tell S1 to D1, he brings 16 rupees to the company. If we assign S2 to third district, he brings 15 rupees to the company. And if the third person is assigned to the second district, he is bringing 15 rupees to the company. And last person is assigned to last district, he is bringing 15 rupees to the company. Okay. So if we add the corresponding cost from this particular table, S1 to 16, then this to this 15, then this to this district 15, and last person to last district 15. If you add all of them, we will get 61. So this is the maximum profit that they can bring to the company. So above than that profit is impossible. We can challenge. So this particular method is called Hungarian method. This type of problems of maximizing the income is called the traveling salesman problem. Okay. So time is up. So with that, I am coming to the end of this program. In another video, I will come with another problem. Okay. So thank you very much, my students. It is really happy to see you here. Okay. So thank you. Thank you really.